Hello everyone, I am Shegufta Hassan from University of Illinois at Urbana-Champaign. Today I am going to present our work, a new fully distributed arbitration-based membership protocol. Failure detectors are an essential part of membership protocols. Incorrect failure detection might cause stale membership list, which might hurt some systems. For example, think of a cloud-based system that consists of total 3 nodes, N1, N2, and N3. Currently, N1 is hosting an application that is controlling something in the outside world. Say, only the node 1 gets partitioned out from the rest of the system, and the rest of the system immediately reacts and relocate the application into node 2. But say node 1 is still alive and it is still controlling the outside world. Such incorrect failure detection timeout will lead to inconsistent outcome. After a failure is detected by a node, distributed systems needs a timeout after which the detecting node can take corrective and recovery actions. Failure detection is important in various parts of distributed systems. For example, replication, microservice orchestration, leader election, etc. Current failure detection methods can be clustered into two main categories. In the first category, there are weakly consistent failure detectors, for example, SWIM, where in the second category, it consists of strongly consistent failure detectors, for example, virtual synchrony. In 2018 EuroSys, we presented a third type of time-based failure detector that ensures time-bounded consistent membership and which is also scalable to data center scale. It ensures that once a failure happens, after a predefined time bound, all members in a group will have a consistent view of a failed node. Service Fabric achieves it by decoupling the failure detection from the failure decision. Service Fabric's unique failure detector scheme relies on a group of central arbitrators shown by the green circle. In our current work, we decentralize Service Fabric's central arbitrator group and propose a safe and consistent arbitrator handoff mechanism. We also propose a new node join protocol that is coherent with the new arbitration strategy. Besides, we present formal proof of correctness and time bound of both approaches. Please note that neither the original Service Fabric paper nor any of its white papers provide the formal proof of time bound. In this slide, I'll very briefly explain the leasing mechanism, which is the main failure detection mechanism used in Microsoft Service Fabric. Here, each pair of neighboring nodes, node P and node Q, maintains symmetric leases, LPQ and LQP. This slide covers the lease LPQ. Here, TL is the leasing interval. Now, for each such interval, node P periodically sends lease request to establish the lease from node Q. Once node P receives the corresponding ACK, the lease for that time slot is marked as established. However, in case of a lease failure, node P marks node Q as failed at the beginning of the next interval. We theoretically proved that the failure detection time TFD is bounded between TL to twice TL. We also proved that the timeout interval between two symmetric leases can be at most twice TL plus TA, where TA is the arbitration timeout that I will cover in my next slide. In this slide, I will briefly cover how the centralized arbitration-based mechanism works. In case of a lease failure, both node P and node Q will independently send arbitration requests to the centralized arbitrator group. If either of node P or node Q doesn't receive anything from the arbitrator within the arbitration timeout, which is TA, in that case, node P and node Q, the affected node, will gracefully and voluntarily leave the system. Otherwise, each arbitrator node will independently mark the first requester as alive and send back the decision. Only the node having the quorum number of alive messages can stay in the system, and it can safely assume that that after a predefined time bound, the other node, that means the suspected node, will definitely leave the system. We prove that the arbitration request interval between two such suspecting nodes is bounded by TL to 2TL. The centralized arbitration scheme used in Service Fabric can become the central point of failure. If majority of the arbitrator fails, the entire logical ring will collapse. Besides, the arbitrator node requires special deployment. Our current work removes the dependency over the centralized group. It tactically splits the centralized arbitrator's responsibility and equally distributes it across the partially overlapping neighborhood of the ring. Now, I'll very briefly explain how in the decentralized arbitrators approach, this pairwise arbitrator formation happens. But before that, let's consider that in Service Fabric, here each pair of nodes consults with the centralized arbitrator group. It doesn't matter which pair it is, they will always consult with the same group of arbitrator node. In our proposed approach, each neighboring pair maintains a separate arbitrator group. In this example, neighborhood count n equals to 2. That means this node, say for example node 20, will have 2 nodes in the clockwise direction and 2 nodes in the anti-clockwise direction. So it will have total 4 neighbors. For lease L20 and 18, which is happening between node 20 and 18, node 20 maintains an arbitrator group for node 18. That arbitrator group consists of both node 20, node 18, and all of their neighbors. For the pair PQ, the symmetric leases are LPQ and LQP. Now, both of these leases independently maintain two arbitrator groups, APQ and AQP. These two symmetric arbitrator groups must be consistent. For example, if node P's neighbor node, node O fails, and then node N becomes a new neighbor, and in that case, P cannot immediately change its arbitrator group. To modify the arbitrator group, node P needs to initiate an arbitration handoff protocol. The arbitration handoff is a two-phase protocol where the first phase is propose and the next phase is an optional propagate phase. In phase 1, node P propagates or propose the modified arbitration group to the old arbitrator group. There can be 3 possible outcomes. In the first case, majority of the arbitration request might time out. In that case, P will leave the system. In the second case, majority of the arbitrator might reject P's arbitration change request. In such case, P will simply stick to its existing or current arbitrator group. In the last approach, in the last case, the majority of the arbitrators approves P's arbitrator change request. In that case, node P will change to the new group and it will explicitly send a notification about the change to node Q. And in phase 2, it is optional where, if successful, then node P in its next lease from node P to node Q will piggyback the arbitrator change information. We prove that the maximum possible time where such symmetric arbitrators can be inconsistent is twice TL. Next theorem is one of the main contributions of this paper that proves that once node Q fails, after the next TA plus 4 TL time units, all of Q's members will consistently know about it. Besides, if node Q gets partitioned out, even in that case, after that interval, node Q will voluntarily leave the system. Therefore, after waiting for that interval, it is totally safe to mark node Q as failed node and reallocate its resources. This is the core property of Service Fabric's leader election algorithm. Now I will very briefly explain the node join protocol that we are using in our decentralized arbitration scheme. This node join is a 4-phase protocol where in phase 1, it is the neighbor discovery phase, phase 2 is the lock request phase 3 is the lease invitation phase, and phase 4 is the wrap-up phase. In the first phase, the candidate node C, first send a neighbor discovery message and figure out its twice n neighbors, n in the clockwise direction and n in the anti-clockwise direction. In the next phase, the candidate node tries to acquire locks from all of its potential neighbors. In phase 3, it initiates the symmetric leases. And in phase 4, it consistently adjusts the new arbitrator group and wraps up the node join process. Here in this slide, I'm giving a very high level overview. For details, please check the paper. Now I will present few evaluations from the paper. In this paper, we prove the failure detection timeout. We perform an experiment to empirically validate our proof. We deploy a 64-node cluster in EmuLab, perform various experiments with different leasing intervals shown by the x-axis. So in some case, the leasing interval was say 32 milliseconds, whereas in some other case, it was 128 milliseconds and so on. We introduce failure, and the y-axis measures the failure detection time normalized with respect to the leasing timeout or TL. This plot shows that our empirical data of the failure detection time is coherent with the theorem where on average the failure detection time is 1.5 times the leasing interval or TL. We set up a simulation with 1000 nodes and measure how decentralizing the arbitrators reduce the arbitrator's load. In this experiment, neighbors count per direction n equals to 3, and we simultaneously kill f equals to 100 nodes. Therefore, in the centralized scheme, for this f number of failures, each arbitrator receives twice n into f, or in this example, 600 messages. Let's see how much message a single arbitrator receives in the decentralized version. In the decentralized scheme, as the load is now distributed, for the same number of failure, each of these arbitrators will receive, even in the worst case, at most only 24 messages. In this experiment, we measure the node join latency and scalability of the node join protocol. Here, n equals to neighbor count in each direction, and j is a total number of nodes try to join simultaneously. We vary the ring size shown by the x-axis. The y-axis shows the node join latency normalized with respect to TL. This graph shows that as the ring size grows, it causes less conflict, and therefore newly joined node can easily enter or join into the system. And it also shows that the new node join protocol is highly scalable. In this experiment, we measure the impacts of node failure. We deploy both the centralized version marked by CA and the decentralized version marked by DA. The centralized version relies on total 5 arbitrator nodes. For both CA and DA, the x-axis shows the total number of failed nodes. The y-axis shows the remaining nodes in the entire ring. The centralized setup consists of total 5 arbitrators that's been shown by the dotted black line with the triangles. From this graph, we can see that for the centralized version, when majority of the arbitrator fails, in that case, which is 3, the entire ring collapses. However, in the decentralized version, as it doesn't rely on any special group, the node failure doesn't impact the entire ring. So in this presentation, I have given a very high-level overview of our work in new fully distributed arbitration-based membership protocol, where we decentralize Service Fabric's central arbitrator group and propose a safe and consistent arbitrator handoff mechanism. We also propose a new node join protocol that is coherent with the new arbitration strategy. Besides, we present a formal proof of correctness and time bound of both approaches. Please note that neither the original service fabric paper nor any of its white paper provide the formal proof or the time bound. With this slide, I am concluding my presentation. Thank you.